מתק הזה של אור לוקס.
הייתה לי גם שאלה על about the material, the last
Okay, go on.
lecture.
Yeah.
So we said in the last lecture that the Laplacian is I minus P. Identity minus the condition operator.
Yeah.
And you can see that if the green function, the green operator wants to be like an inverse.
Yes.
To the Laplacian.
Well, that's an exercise I didn't give yet. Yeah. Okay.
But so I was thinking, if for some function you take you operate with the green function operator on this function, you take the sum, and it converges. Then it means that for this function, it cannot be harmonic function. I was thinking that if the Laplacian has an inverse, really has an inverse, then its kernel is empty.
So what you have to be very, very careful about is what's these spaces. These things are not, we're not talking about operators on specific spaces. Usually typically what happens is the Laplacian will map. So if you restrict yourself to L2, everything is fine. Well, not for the green function, but you can talk about, this is called the bubble condition, for reasons I will not describe now. But the bubble condition is equivalent to the following condition. The green function is an operator on L2. So you can speak about these things in many, many cases. In fact, you can classify all the groups for which the green function is not an operator on L2. Most of the groups, the high dimensional groups, the green function will take L2 functions to L2 functions. And we will talk about this a bit in the future. But in general, when we speak of harmonic functions like today, when we're going to talk about polynomially growing harmonic functions, we're talking about unbounded harmonic functions, definitely not in L2, definitely not in LP, definitely not in some nice normed space. So it's a problem to speak about operators. So the only thing that makes these operators is that they're linear. And it's not clear what the original space is and what the image is, right? So there's no operator theory to use. So everything you're used to should be you should have to be very careful if you want to apply like some idea from linear algebra, because it's not clear that which space is being mapped into which space. That being said, it is true that if you have a function such that you can operate on the green function, then that function will typically not be harmonic. Have to be careful because it could.
Did we talk about how the green function operates on functions?
So I'll review what in general what operators mean in this case, what matrices mean in this case. So basically, it's just countable sets with things indexed by two. Okay, so maybe we go into that. I don't want to go into all the subtle details.
From perspective that things that we didn't talk about yet, but we know that convergence of the green function, the green function for some x and y is related to transients.
Yes.
And transient.
Well, we basically proved that the convergence of the green function.
So, and transients is, you do expect to have harmonic functions when the group is transient, not when it's recurrent.
What harmonic functions? No, you always have harmonic functions that you're thinking of, but bounded harmonic functions, you don't have it just by transients. ZD does not have bounded harmonic functions.
Yeah, I know, but you expect, in recurrent groups, you don't find them at all, right? Oh. Sorry, not bounded harmonic functions, you don't.
But the Lipschitz harmonic functions, you do even in recurrent.
Yeah.
So as soon as, the recurrence and transients do not play a role in the unbounded harmonic function theory. Recurrence plays a certain role in harmonic function theory, in bounded harmonic function theory, but it's not really playing a role because anything generalizes to it's part of a, you can prove it in an easier way, but it's part of it more than.
Not exactly right to think about convergence of the Green theorem as being opposed to having harmonic functions.
Subharmonic functions or superharmonic, one of them. Recurrence is equivalent to the existence of a non-negative sub or superharmonic function, and I need to check which one it is. But basically, one of the directions. I always forget what it is, but we can phrase a statement. But what you're doing now is spoiler. Sorry. Transience is equivalent to the existence of a function such that, well, basically the green function is a sub or superharmonic function. So recurrent transience is equivalent to the existence of whatever the green function is. Green function is non-negative. It's the expected number of visits, right? It's a non-negative function. I mean, you fix some base point. Expect the number of visits to a point. So it's a function of the base point, of the starting point, right? And you fix the expected number of visits to the origin, right? So if you're transient, that's a well-defined function. This is going to be almost harmonic. It's not harmonic at the origin. And then you'll check that it's a non-negative sub or superharmonic, whatever one comes out. And that's equivalent, the existence of such a function is equivalent, non-constant one, is equivalent to transient. So in a recurrent Markov chain, in fact, recurrent connected Markov chain, every non-negative other sub or super will be constant. Okay, so that's the one that goes with recurrence and transience. Is different. I hope we get to talk about recurrence and transience. Okay, today. So now I want to remind you. Suppose I have a matrix. What is a matrix? A matrix is just a function from G to G to R, maybe even to C. Okay, right? You just index the entries of this guy by the entries of G. And specifically, we saw a few of them, right? We saw P, X, Y, right? This was the probability starting from X, that at one move I jump to Y, right? The transition matrix of a Markov chain. So that's a matrix. We saw another matrix that was now mentioned, which was GXY. This was the expected number of visits to Y. Yeah, we can write it like this. PTXY, and remember we saw that this thing, well, this doesn't necessarily have to converge. We can talk about when it converges, and if it converges, this thing is a well-defined matrix, whatever, and we saw that it's exactly the expected number of visits to Y starting at X. It just counts. What?
Not the green function.
This is the green function.
No, the GL.
It's sum over T, not
Yes,
over Y.
okay.
Counting number of visits, X and Y are fixed. Okay, so is that what you meant, that I need to do the special G? Yeah. Yeah, I might forget to do the special G sometimes, but so this is the green function. This is just what we done. It doesn't always converge. This is always, I mean, we always talk about the situations where this is defined. See, this can explode. Now, how do such things act on functions? How do they operate on functions? So they are linear operators. So functions are vectors, and these are matrices, and they act exactly like you would expect them to act if G were finite. Okay, so if you have a matrix A and you have a function, and you want, so it gives you a new, so matrix acting on a vector gives you a new vector, right? And it just acts. You want to know what it does at X, so you sum over all the Y's. You take the X row of A, right? You go over these, and then you multiply by f of Y, and of course, you have to check that this is a well-defined object. For example, let's decide from now on that we never write this down if this sum doesn't converge absolutely. Okay? Only for absolutely converging sums will we use matrices acting on vectors. Okay? Or matrices acting on functions. Okay? So if this sum doesn't converge absolutely, then it doesn't play into our discussion. We can start defining spaces and it just makes a mess of everything. Okay. So if I write something like this, I'm implicitly assuming that it converges absolutely. Okay, or if I write AF, I'm implicitly assuming that at every x it converges absolutely. Okay. For example, we had the Laplacian, which we defined as just the identity operator minus p, right? And then we define definition f is harmonic at x. And now if this Laplacian came from a mu, then we would say f is mu harmonic. But in general, harmonic means with respect to what? With respect to some transition matrix, which defines a Laplacian, which gives us this. We saw the motivation for defining this, right? The integration by parts formula. But f is harmonic at x if Laplacian fx converges absolutely. Usually I will not specify specifically that this happens. So again, when I'm writing this down, it means I assume that it happens. Not only does it converge absolutely, and it's equal to 0 at x. So this is being harmonic at x. Okay? Harmonic on a set means you're harmonic in every x in the set, and harmonic in general, okay? So let's say harmonic in a set A. I used A for an operator and A for a set. Okay. This is the same thing as saying harmonic at x in A for every x in A. Harmonic at x for every x in A. Okay. And harmonic in general, I just say f is harmonic. This is the same as for every x in G. Okay, so I mean, these make sense. Now, someone asked me last time, what does this have to do with the mean value property? So remember in classical analysis, when you have a harmonic function, you could define harmonicity by this being 0. Okay, function is harmonic. You have to specify domains in classical, but anyway, so in some open set, okay, this happens, right? Or you think of this operator as the sum of the partial second derivatives, right? Okay, if you don't know what I'm talking about, you can forget it, but that's what you do in, I don't know, calculus 3 or 4.
Not mixed second derivatives, right?
Not mixed, diagonals. Yeah. Okay, it's the gradient dot product with the divergence, so it exactly is the diagonal, right? Because dot product. Mixed will be the Hessian, and it's a matrix, and it's something else completely. It's a different object. But you also know that, I mean, these are classical theorems, right? So f is harmonic in so f will be harmonic. So f will be harmonic in some open set U, right? And in some open set U, if and only if for every a small enough epsilon in every x in U, so epsilon has to be small enough, maybe depending on x, but anyway, for every x and for every epsilon small enough, which could depend on x, because you need the ball to be the ball radius epsilon to go into to mu. The integral, when you integrate around the ball of radius epsilon around f, so this integral is on bx epsilon boundary. So you're integrating over, this is a in a sense a d-1 dimensional, whatever dimension this is living in. You're a d-1 dimensional integral. You're integrating over the sphere, okay? And you look at the values of the function. If epsilon is small enough, you can f is defined. So the values of those functions, dy, whatever. I'll write nu y here. Nu is the surface measure. You have to understand what that is. And so if you integrate all of these things, what you get is f of, you just get the same value. So the average on the ball, in a sense, we have to divide by well, it depends what nu is. Okay. So you think of nu as normalized to be a probability measure. Yeah. I mean, for me, it's easier to think of it this way. Okay. So you just take the average value. So what is harmonicity in the plane? Harmonicity in the plane or in the complex plane, which also gives you all the beautiful results in the complex plane because of the symmetries of two dimensions. But this is a general fact for d dimensions. You integrate, if you have a function which is harmonic in some domain here, and you take a point, then it's equivalent. Saying that it's harmonic at x is equivalent to saying that if you take a small enough ball around x and you average the values of f here, you get the number here. The average on the ball is the number in the center. Okay? So it's kind of satisfying certain restrictions. And these things have a physical meaning. The reason people looked at these things is because they have a physical meaning. Okay? It has to do with waves, drums, and I don't know, something. No, I mean, yeah, really. I mean, yeah, it's harmonic analysis. Yeah, well, we're also doing harmonic analysis, but this doesn't have any physical meaning. Not very much. So, the people already were looking at this in the 19th century. I mean, these are classical objects. I mean, Cauchy and Liouville and all the names I could say. So this is what harmonic means now, and now we can define a harmonic function in general. It could be unbounded, it could be crazy, it could grow exponentially, it could be giant, right? It really could go crazy. Okay. It could be complex value. I mean, everything here we could talk about complex value in harmonic function, right? Saying something is converged. Maybe I should have written that. Okay. Just to make sure. Okay. We ever want to move over algebraically closed sectors. So, but basically you should think of this as the operator. So what does this operator do? What does P do? What does P? When you take P and you operate on an F, I wanted to say, what's the analog of this? So when P operates on a function F at a point X, assuming that everything converges nicely, what are you doing? You're summing P, X, Y, F of Y. So what are you doing? You're looking at X, you're jumping randomly to Y, and you're averaging what the value you would get. This is exactly the expectation starting at X of F applying to the first step of your random walk or your Markov chain. So you're averaging the value of F, right? This is just how you take averages, right? You have this random variable gets this value with this probability through this measure. Okay? I mean, just discrete random variable. I mean, it has accountably many values at most. Okay, because there are only countably many options for what to plug into the function. Okay, so it's just a discrete random variable computation, and you get it. Of course, if it converges absolutely, this makes sense. It could happen not to converge absolutely. So then we don't talk about it. But if it converges absolutely, which just means that under this measure, this is an L1 function, L1 random variable, right? Then we have this. So you see, you're averaging the function around the point X. That's what you're doing. And harmonicity is exactly the condition. What is harmonicity? Harmonicity is that the Laplacian is equal to 0, which means what is I acting on F? I acting on F is F. And then you have I minus P is O acting on F is 0 is the same as F is equal to, because again, everything is converging absolutely. I can move things to the other side. F is equal to Fx. So this is exactly the mean value property. So I hope I convinced you that both of these things, last time we talked about this representation, now we're talking about the mean value representation. Mean value is easier to think about when you're talking about these random processes. It's actually easier to think about, I think even in classical analysis, it's easier to use mean value property sometimes, except for actual computations. Why? Because in actual computations, integrating little balls and everything and taking derivatives is easier, right? You always know how to do the derivative somehow. Integrating is hard. Taking derivatives is easy. Here we don't have the luxury of taking derivatives. Like here, taking derivatives is hard. Averaging is easy. Okay? The opposite for discrete analysis. Maybe it's because L2 and LP go in the other direction. And Double sets? No, that has nothing to do. It just, discrete world is different from the continuous world. When you can't shrink distances to zero, things become, have to carry error terms, and so it's very hard to take derivatives. There, everything will vanish. Very easy to understand derivatives. Okay? Good. Yeah. So, for example, if you want to compute the green function on the lattice, so Z3, the green function converges. I'm not going to prove it. Z3 with the standard generators, okay? And standard cubic lattice, three-dimensional generalization of this.
Transient?
Yeah, so it's transient, and you can compute. Maybe we'll talk about it if we have enough time. So Z3 is transient and has a green function. We didn't say what transient is, so we might talk about it in the future if we have time. But so computing the function, the green function here is actually quite difficult, and you can expand it asymptotically, but it's exact form. There's no nice formula, and you get better and better approximations or things like that. It's roughly on Z3, so roughly gxy in this graph. Okay,
Right now,
This
the integrals are easy.
this is done in the okay. So okay, so it's not easy. So gxy, so this is roughly in what sense? I'm not going to say. Okay, some constant which depends on the dimension. I'm going to write d here, even though it's 3, but you can think of why it's also true for. I mean, this is true for higher dimensions, and then it's roughly going to be the norm of the distance between x and y, 2 minus d, where d is the dimension, so it's -1 if d is 3. Okay, so you can see why I need d bigger than 2 for this to work. Okay, so this is true. Okay, what this means is the ratio between there is a constant depending on d, so the ratio between these will go to 1 as the distance goes to infinity. Okay, the next term will be smaller. That's kind of, and even this is a very hard theorem. Even this is a very hard theorem. I mean, it's not trivial to prove at all. Okay, even bounding between two constants is not trivial. Okay, in classical analysis, so if I were to work in R3, okay, then it's quite easy. Few lines to show. You just need some other characterization of the green function, which I will give you as an exercise actually, and it's quite easy to show that the function that takes a vector to this 2 minus d in Rd will be the green function. The green function is translation invariant, so it only depends on the difference between the two. Remember we said it's left invariant, right? Because so this is quite easy. Much easier in the continuous case.
But we actually define the green function in continuous.
Yeah, so you'll see soon that the green function, well, I'll give you an exercise at some point. The green function is a solution to an equation with the Laplacian. Okay. I need to phrase the exercise properly. But basically, okay, well, I'll say one more word. You will have this exercise in the future, so you can think about it. So suppose the green function converges. Suppose everything is nice, and in fact, suppose more than the green function. I mean, somehow suppose that you're in a nice enough situation, maybe high enough dimension or something like that. Then what you want to say is that so we can define, okay, so we have this green function. Let's define yeah, so let's fix some x, and let's define a new function gx. Okay, sorry, gy. So this will just be gy of x will just be gxy. So it's a function of the starting point where the visiting point is fixed. Okay. My claim is that the Laplacian applied gy is what? Well, we can think about it. Okay. So now this is a function Y is fixed, so I'm applying only to the starting point. So what is it? Well, the expected number of visits to Y, let's use the Markov problem. How many times do I visit Y? It could be that I am at Y at time 0, if X is equal to Y, right? And then I get one visit for free, right? Because I count time 0. But then I take a random step. And how many visits am I going to visit Y in expectation? Well, I have to, either I moved here, just a law of total probability, right? So it's the average of the number of times I'll visit Y starting from each one of the steps. Okay? That's not a proof, that's a description of how to prove this, but basically what you get is that, so the equation you're going to get is that GY is 1, if you're at Y, a delta Y function, right? Plus average the next number of steps and ask for the number of visits. What's the average? The average is taking P. P averages, right? P averages the next step. That's what P does. Okay? We have to think why this is true. But you see, now I have I minus P is delta Y. So this is just telling you this is the same as saying that the Laplacian dy is equal to delta Y. So this is the defining characterization of a green function. It's a function such that, or you do it for delta 1, and maybe you can translate if you're in a group, or maybe you have to do it separately for every Y. But it's kind of a function for a specific Y. The green function at Y would be the function which solves that equation. The question is, can you even solve that equation? Okay? I mean, in fact, the question of solving this equation was one of the things that Green was trying to do when he defined, when he proved all of his theorems. Because if you solve this, then you can kind of solve, right? And the more general situation is you want to solve, you have some boundary conditions U, and you want to solve something like Laplace. You want to solve for Laplacian f equals U. Right? U is you have the values on the boundary maybe, okay, or you know what U is, and you want. There are lots of we could discuss this. It has to do also with harmonic functions, but and the different road. Okay, so if you know how to solve this kind of, you see how do I get a specific U here? Well, I just sum over all the delta Y's times UY, and so I use the fact that this is a linear operator. All these matrices are acting linearly, right? So linearly in the following sense, we don't have an actual vector space, but if you know that this operator, for example, or the Laplacian converge on converge absolutely for every point when I act on two functions, f and f prime, then I can take a linear combination of those two functions, and the action on the linear combination will be the linear combination of the actions. So it's a linear operator, which is just linearity of expectation, if you think about it. Just linearity of expectation.
Since you can decompose any function to a linear combination of delta functions.
Well, any finitely supported function.
Yes, but in physics you can do it even for on RD, on R prime. Then this is the importance of the green function.
Yes. No, so that's what Green. This is what Green was doing. All the theorems you learned that were done by Green and Stokes and all those things, they are solve differential equations of this type. Laplacian, something equal in a sense. And it all boils down to solving Laplacian f equals delta y. That's what it boils down to. Which functions? Does there exist a function, and does it solve? Green proved that there exists one, so it's called the Green function. Some people say Green's function, right? But I don't know. I get used to saying the Green function. Okay, but again, defining the Green function in general. In fact, sometimes what is delta even, right? What is delta in continuous space? So defining it in RD is much more difficult. So in a sense, it's much easier, even when talking about it.
Even without the delta function, what you prove instead is that to get the solution to some more complicated to another partial differential equation, you just need to integrate against the Green function. It's like a kernel to get you the solution when you have the boundary condition.
Yeah, so you get a kernel. Okay, this is exactly the theory of matrices, and we put that theory in.
Yeah.
We don't share the kernel.
It's like a kernel, yeah.
Well, a kernel is just a matrix in continuous space. what we said as a matrix is just a function with two things, right? So now you want to, what is a kernel? A kernel is just when those two things are not countable. You have to be careful. There's measure things that come inside, zero measure, measurability, all messes of things. But basically, that's the way you should think about it. It's just a way of specifying how an operator would act. In matrix, you just tell me which numbers, and in a sense, you fix the basis when you told me those numbers. The basis is the delta functions. When you want to do a kernel, the delta functions are not even functions. So what does it mean to fix a basis? You know, so. And in fact, Fourier analysis, in a sense, is saying, oh, there's a nice basis I can work with to define kernels. And the theory of kernels is kind of, oh, when I don't have this nice basis, not a Hilbert space, I don't have a nice basis. So what can I do? How can I abstractly give properties of kernels? So that's kind of it. It's just a generalization where you have to be careful of how you define things, or you're a physicist and you're not careful and you just say it. And then you get a paradox. At some point you get a paradox. Okay, so let me define a space. Let me define a space. Definition. Do this today and another day we do. So I'm going to show you how martingales help us. Optional stopping theorem, martingale convergence. We're going to use them all the time to prove things about harmonic functions. So G is going to be a finitely generated group. And mu is going to come from symmetric adapted exponential tails. Everything I say can be generalized, but then proofs become more difficult. You can make it relax the conditions. We'll work with exponential tails. I should have worked with finite support, I told you. We'll see today why I want to work with infinite support, but at least with some nice condition. Okay? So, okay. So we define the space HFK G mu. Okay? HFK G mu is going to be defined to be HF is harmonic function. Okay? But not bounded. So HFK, this is going to be the functions. All the functions from G to C such that there exists some constant such that for every x in G, f of x, absolute value is at most x plus 1 a times c. This constant can depend on specifically on f. All this means is basically that f doesn't grow faster than a polynomial of degree k. What is this guy? Didn't say what that guy is. Fix some telegraph. Okay. By the way, when I say infinity, it means that there is some K-graph in the background. We said that it doesn't depend on the specific set of generators, right? So putting an absolute value on a group element, you have to be careful. That means there is some K-graph fixed in the background. If I change the K-graph, we said that this only changes by a constant, right? They're bounded, each constant's bound each other. So it just changes this C, but it doesn't change the fact that there exists a C such that this property happens for all x. Okay, so even if I fix the K-graph, so definition of this space does not depend on the specific K-graph. It stays the same space for the same mu. It does depend very strongly on mu.
They don't write harmonic.
Now, first of all, you can tell me, why did you write this? Maybe it doesn't converge absolutely. One, I said when I write it, I mean that it converges absolutely. Two, it will converge absolutely just because of this condition and this condition. And the reason you should think about it is because when you're averaging with mu, the far away guys are decaying exponentially. That's what this infinity means, right? Going far away has exponentially small probability. That's what we said infinity means. I'm going to remind you that in a second. And this is only growing polynomial. In worst case, you're summing a polynomial against something decaying exponentially, it's going to be an absolutely convergent sum. Okay, so that's a fact, and I'm not going to prove it, but you can convince yourselves that that's true. You prove that any function that lives in this space, the Laplacian will converge absolutely, and then so I can take the harmonic ones. Okay, harmonic functions, polynomial degree k. What does k equals 0 mean? Yes. If I h k equals 0, then this is just some constant, right? So all it says is there exists a constant such that all the things are bounded by that constant. So they're just bounded harmonic functions. Okay? So this I also like to write BHF G mu, just to remind us it's bounded harmonic functions. Okay? Now, first of all, I claim that all these spaces are vector spaces. Exercise, these are vector spaces. Just means that they're closed under linear combinations with complex scalars. Okay? That's one. Two, they're non-trivial. Okay, so if I said they're vector space, they're non-trivial. The zero function is definitely inside them, but they're not only the zero function, they always have dimension at least one, because constant functions are always harmonic. Okay, that's not like giving an exercise. I mean, you can easily see that a constant function is always harmonic. Okay, so all the constants live inside these spaces, right? And in fact, they live inside one inside the other, right? So bounded harmonic functions, G mu, is a subspace of HF1 G mu, which is a subspace of HF2 G mu. I mean, I could also do in between, right? But anyway.
With like an infinity sense?
What?
Check.
I didn't understand. You said Trinity? Trinity is.
No, I said infinity. It's like unbounded infinity.
Yeah, we could write just a set of all harmonic functions. We could also talk about that. That's also sometimes interesting, but I won't talk about it. I want to put some conditions that guarantee that the Laplacians converge absolutely, so I don't have to worry. And, yeah, I could, but we could definitely talk about HF epsilon harmonic functions. We could talk about harmonic functions even smaller than HF epsilon for every epsilon. I could talk about, we could define many spaces.
Can they go more rapidly than polynomially?
Yes, of course they can. They can grow exponentially. They can grow super exponentially. Yes. Okay. One more thing that I want to do is I want to talk about Lipschitz harmonic functions. I might want to, well, I will talk about these in the future. This is a subspace of the HF1s. The HF1s are the ones that grow in a linear fashion. Saying that something grows linearly is not as strong as saying that something grows Lipschitz. Lipschitz means that between any 2 points, linearly is with respect to the origin, right? Because this is measuring distance with respect to the origin. So Lipschitz HF G mu is, I can write it this way. It's all they always come from the linear ones, because if you're Lipschitz, you're linear. But I have the restriction that f of x minus f of y is less than or equal to some constant times the distance between x and y, which we can write this way. So you see, this is stronger. This is a stronger condition than this with k equals 1, because, so there exists C. Okay, this is a stronger condition than HF1, because you see, if I take y equals 1, right, then this is just some constant, the additive constant, and this will be just the absolute value of x. Okay, so so this. I mean, I could have defined all the functions such that there exists such a constant, of course, for every x and y, and also such that they're harmonic, but this will always live inside HF1. So I just take so just remember that there is such a thing as Lipschitz harmonic functions. We will talk about that in the future. I mean, it might be interesting. I have some interesting open questions. Difference between this and HF1. They are not the same space. They're not always the same space. Even on groups, okay? And a basic question would be, one of the guiding questions maybe, would be, how do these spaces change when you change this little thing? What happens to the spaces? For example, maybe the dimension, change or not? Okay, these are vector spaces, and that's what dimension is. We'll see, we'll talk about that question in the future. Another, more basic question is, are these spaces even not one-dimensional? So we said they're always at least one-dimensional because they have the constants inside them. But maybe they have more. Do they have any interesting harmonic function, non-trivial harmonic? So when I say non-trivial harmonic function, I mean a non-constant one. Okay? And we'll see actually that the answer is yes. Every group, symmetric adapted exponential tail measure, meets a Lipschitz harmonic, a non-constant Lipschitz harmonic function. There always exists a Lipschitz. We'll prove that. It'll take us some time to develop. We'll have to go through Hilbert spaces to prove it. Okay. And but it's not true that every group has a bounded harmonic, non-trivial bounded. In fact, I will try to talk about which ones, some that do and don't. Okay. So so maybe we start first with what do we want to do? Okay, maybe I'll show you something that has to do with that. So do you remember the action on functions? In general, if you have a group, did we talk about group actions at all? We didn't talk about group actions, right? Okay. Maybe I don't want to talk too much about group actions. Let's define. So the group can be thought of a linear operator. The elements of the group can be thought of linear operators on the space of functions of the group. Okay, so if f is a function from G to the complex numbers, okay, and x is an element in G, then we can define a new function x dot f. This is not product, this is dot period. Okay, little dot here. This is a new function from G, C, and we define it. I have to tell you what this function does at a point y. Okay, what it does is it just looks at the old function by translating by x. Translating by x. This gives us a new function. Right? X is fixed, it's a function of y. Good. What happens? We can ask, I mean, okay, so this is a group action in the sense that what I've done here, okay, so this is a linear, you can check that X acts as a linear operator on the space of functions. So the space of all functions on the group is a vector space, and this acts linearly. So X acting on alpha F plus F prime is the same function as alpha times X acting on F plus X acting on F prime. Right? The same thing. I mean, you just check it, but it's just very, very. Okay, so what we've basically done is we've defined a homomorphism, a group homomorphism from elements of G into linear operators on the space of functions on G. Okay, it's a homomorphism. You can check that if, okay, so you can also check that if I do X acts on Y acts on F, this is the same, right? So this is a function, I can act on it again. This is the same as X, Y acting on F. Here I first multiply, then I act. Okay, so that's the same thing. Just very easy to check. That's why I also put the -1 here. It's called a left action because I'm acting from the left. If I didn't put the -1, it would be a right action. So what would happen is that these would go in the other direction. X would be first and then Y. This way it's kind of compatible in the notation, so you put the -1. Okay?
If it was a right action, it wouldn't be a homomorphism, right?
It would. Would be, but it would just be acting from the right. You have to think of operators acting morphism into a different there are many left and many right actions you can define. Another thing you can check is, of course, well, this also tells you that every one of these operators has an inverse, right? Because if x and y are inverses, you get the true. So basically what I'm saying is that 1 dot f is f, right? 1 acts trivially well, you can see that. Okay, so you get the same function. So this is a way of acting on a function. This is very, very classical. Of course, there are other ways of acting. I'm not going to, maybe we'll go into them in the future. So this way of acting on functions, well, what does it do to a harmonic function? Exercise, I want you to see, is that for any f in HFK G mu, x dot, and for any x in G, x dot f is also in HFK G. Okay, I have to be careful because this function grows polynomially what? When I measure distances from the origin. This function is going to grow polynomially when I measure distances from x. What this is doing. And or x minus 1 or something like that. And then you have to understand why it still grows polynomially from the origin. Well, it's basically because x is fixed, okay? X is fixed. You have another finite distance that you need to go to the origin, okay? You have to be careful with this proof. And it's also true if I would replace HF by Lipschitz, right? So we keep the Lipschitz property, Even if I wrote LHF here, then I would write LHF.
The different properties without this is more explicitly.
Yeah, it's more explicit. The constant will not change because the Lipschitz is everywhere. Okay. And in fact, actually what's going on is that all of these spaces can be defined by a semi-norm. Not a norm, but a semi-norm. Okay, there are the spaces for which some semi-norm is finite. You could think about what the norm is, what the semi-norm is. And the semi-norm is just a norm, but without the restriction that if the norm is 0, then the function is 0.
No, it's one semi-norm or semi.
No. So for each K or Lipschitz, for each one of these spaces, and for the Lipschitz, you will have a different semi-norm. It will be the space of all functions such that that semi-norm is finite. And the semi-norm will be invariant to the action. So XF will have the same norm as F.
That's another way.
So that's another way of showing that these things. Okay. The way I defined them was a bit different. Okay. So the theorem I want to prove, which we will do after the break, is the following theorem. I want to relate. So theorem, I'm going to be not exact, but just tell you what's going on. Is I want to relate the space HFK G mu. It's going to be isomorphic as vector spaces to the space HFK H mu H, where H is some finite index subgroup, and mu H is some probability measure. It comes from U, but it's a probability measure on H. Okay, so I want to show you that moving to finite index subgroups is possible. You might have to change your measure a bit. You might have to do some work, but you'll get the same structure in terms of harmonic functions. Okay, that's one thing that I want to do. But maybe before that, we'll say something about the dimension of bounded harmonic functions. Okay, so before we go into it. Okay, so let's take a 10-minute break and then.
כן, בכל זאת, הייתי היום לא בלילה.
אותי רק על שאלה 2. אבל האמת שדווקא לא על החלק הראשון.
So let's first see something about dimension of harmonic functions and see how martingales give nice solution. Theorem. Mention bounded harmonic functions G mu. So mu is going to be symmetric adapted. But in fact, probably we don't need this restriction, but we'll see in a second. But what do we need? Okay. So the dimension of bounded harmonic function, well, this is at least one, right? As we said, the constants are there. And the claim is that this is in one or infinity. So as soon as you have one non-trivial one, you have an infinite dimension of them. Okay?
Wait, this is true for, if you take harmonic functions on Z, I think you only have ax plus b and constant functions, right?
So it's one.
Two dimension, because you can take
X plus b is not, ax plus b is not a bounded harmonic function.
oh, sorry, talking about bounded.
Bounded harmonic. Okay. So, proof. So what is the proof? So let's assume for contradiction that this dimension, I mean, I'll write the G mu all the time, okay? We know which G mu we're talking about. We're assuming it's finite, but strictly bigger than one. Meaning we have a non-constant bounded harmonic function inside this space, okay? No, I don't need this. Assume, not for a country, let's do it constructively. Assume that the dimension is finite, okay? I will show you that every bounded harmonic function is constant. Okay. Now, so these functions, there's a basis. There's a finite dimensional basis of functions, right? And any two functions which are different, there is a point at which they have to be different, right? That's what it means for two functions to be different. So I can find a finite set which differentiates between any two basis functions, right? Finitely many basis functions. This means that I can take a large enough finite set such that any two functions in my space, since they're all linear combinations, right, have to be different on some point in that set. Okay, so the fact that the dimension is finite, this implies that there exists a finite set B such that if the restriction of F is the same, restricted to B, it's the same as the restriction of, say, H restricted to B, then actually H and F are the same thing everywhere. Okay? It's enough to see the points at B. Why? You write this as a linear combination, you write this as a linear combination, you move the things to the other side, you have a linear combination equal to 0 on B, but we said that the basis, right, we can differentiate between any 2 points, so if it's equal to 0, it means that the coefficients are 0. Okay?
I'm not sure I see why you can differentiate between any two basic functions.
Yeah,
But when you get
then
the
you have the
finite
span.
set that differentiates, right, but you're allowing some linear combinations with
So-
constants that.
So what does this mean? So this is the same thing because of linearity. This is, okay. So you want me to prove this thing? So let's do it quickly. Suppose I have a function whose restriction to B is 0. This means I can write it as some, let's say fj's are the basis, right? And I know that this is 0 for every j, right? For every x in B. Okay, now, I want to say here.
You know, you can differentiate, there's some point that differentiates fj from zero, but what about the constant?
Yeah, so, no, so, sorry, so.
We need to.
So. No, you don't need to use harmonic. This is just true. You have a finite dimensional space of functions. Then there is a finite set on which you see, what is the best way to convince you of this?
Polynomials, it's not.
What?
Polynomials, say. Over R, I mean,
No,
something.
I'm using the fact that this set is, that this is a countable set. Using the fact that it's a countable set. What is the reason for this is true? Because the delta functions are a basis of functions, you know. So if you would have a big, if you would have a, so you have a big enough set which already has, you know, enough dimensions to capture your space. Let me think for a second. Yeah, okay. If I have a set B, right, what did I say?
What is this B?
Well, B is big enough so that for any two basis elements, okay, there exists X in B such that Fix is not equal to Fjx. This is what okay, it's for any two basis elements. Now, what does this mean? This means the map, okay, from this means the map
B to the cardinality is like.
from the space of I want a linear map whose kernel is zero. I want to embed this.
I mean, you said the delta functions are linearly independent, right?
Yeah.
And you have infinitely many of them. So you have to use something about the harmonicity or boundedness or something like that. I mean, boundedness is not enough because delta functions are also bounded.
No, but the space with the delta function is going to be infinite dimensional. That's the thing. I assume that I have a finite dimensional basis. There's a finite set on which I see everything. If you take finitely many delta functions, the set is going to be those points that you go.
Maybe you bring the set of delta function to this space.
Yes, okay, sorry, yeah, exactly. So if I take Fi, okay, where do I want to map Fi to?
Delta functions of all the points of the B, and you like evaluate or something like that. Multiply. And if you multiply, you don't get zero.
No. What I want to do is I think I want to map this to some delta xi. I want to choose some xi so that when I map it to delta xi, this map this extends to a linear map on my whole space because this was the basis. It maps it to a finite set here. And I need to choose the xi properly so that this map what I want to say is that if I have a zero function here, then I have a zero function here.
Maybe you take like all the pairs or something like that.
Okay, let me give you. Let's skip it. This is true. What I said. I mean, I need to think about. it just comes from finite dimensionality. You have finite dimensional set and
Put it in the exercise sheet.
yeah. Okay, I'll think about, I don't know why I'm missing, it's an easy effect and I'm probably just not seeing. There's some finite set such that any two functions are equal on, if they're equal on that set, then, and specifically, this, I can define two norms. One norm is the infinity norm. This is just the superroom. Well, it's going to be a superroom over f of x, right? Remember when we're in a group, this was the actual infinity norm that we defined because the total weight is 1, right? This is defining our bounded harmonic function space, okay? This is actually a norm defining our bounded harmonic function space. But we have another norm, which is the B norm. And define the B norm, which would just be the maximum on B. Okay? And the idea is there is a constant because these space. So this in general for a finite set B is not a norm, semi-norm, but because our space is finite dimensional, it becomes a norm. Because we took B to be big enough so that this happens, this becomes a norm. The only function, in fact, what I should write here, I mean, this is completely equivalent to saying that if the restriction to B is the 0 function, then the function itself is the 0 function. I mean, it's the same thing by linearity, okay? You just have to take a set big enough so that you never see the 0 function and this always happens if you have finite dimensional space, okay? So now we have two norms on a finite dimensional space, and any two norms on a finite dimensional space are equivalent. Okay, so there exists, I mean, one of them is obviously, this one is obviously less than or equal to this one, so I can write that there exists some constant C such that f b times C is at least f infinity, and of course, this is always at least f b for every f. Okay, for every f in my finite dimensional space. Okay, this is just equivalence of norms. In fact, you could easily say that you write the basis and take the maximum constant. This is an easy. Okay. So now that we have equivalence of norms, I'm going to use this important equivalence of norms. So C does not depend on the specific function. And now I'm going to say, okay, suppose I have a function, bounded harmonic function. I want to show it's constant, right? Now, my claim is that f is constant if when I take the infimum over all possible complex numbers, let's call them data, okay? And I look at f minus theta infinity norm, right? What is this? This is exactly 0 if and only if f is a constant function. Right? Because what does this say? This is 0 if there exists a constant such that f is equal to it and non-zero other ones, right? If for every complex number, this infinity norm is not 0, the infimum is not 0. Okay?
Can it be that the norms are decreasing to 0, but never actually 0?
Yeah, but the count space is countable. So at some point you'll get that.
I have to think about it.
Okay? So this is 0 if and only. So we're going to bound this, okay? And this, what I should have said this about the norm. What is the infinity norm when I act on x with some f? Exactly, this preserves the norm. In fact, this is one of the norms I was talking about before that defines this. Actually, a norm, not a semi. For any x, if you shift here, right? What does a shift do? puts another x minus one in here, right? But you still take supremum over all the elements, right? Because it just changes the names of the elements. It doesn't. So it preserves the norm, and we're going to use that fact. So this infimum, okay? This is equal to. So let's look at the. This is going to be the mu random walk. Okay. This is equal to the infimum over all zeta. Okay, if you want to be convinced about the infimum over all zeta, f gets countably many values. The image of f is a countable set. So I can take the infimum only over that countable set. Okay. Okay, so that's why this is going to be 0 if and only if f is constant. But anyway, the infimum over this, I can act on both of these functions. So I can think of this as the constant function. And I can act on it by shifting by x, right? And in fact, I don't want to shift by x, but I want to shift by xt. In fact, I want to shift by xt to the minus 1. Why? That's what I want to do. So this preserves acting on this function, f minus a constant, right? Xt acting on, it's linear, so it's xt acting on f, minus xt acting on a constant is still the same constant. The constant function, okay? Because you don't do anything when you shift the constant function. It's the same function. Okay? Well, this is equal to this just because the action preserves the infinity norm. Then I can use the fact that each one of these is bounded by the B thing, right? So this is bounded by the B norm, which is just writing the following maximum over x in B. I pull out this positive constant C here, right? And then what maximum what of this function at the point little x? What is this function at the point little x? It's f of xtx minus the same constant, because this at the point xtx is just, okay? I'm just taking this maximum. Now I'm taking here the infimum, smallest distance to any number, and I claim that this is less than or equal to just taking a constant here times the maximum of some number here. That number is going to be f of xt. You just think of xt is some fixed. So omega, like the randomness is fixed. I just plugged in something and then I get in pointwise. All these inequalities or equalities are pointwise. Okay? This is because instead of taking infimum over all possible numbers, I took some specific number. Of course, it's bigger than the infimum over all possible numbers. Okay? You're right that there is an issue with that infimum. It has to, the fact that it's countable helps you to understand the following. The set of constant functions is closed. So if your distance to the constant functions is 0, it means you're in the set. And it's not true in general. It's true for countable spaces. You have to think of what the exact conditions are. There's some compactness argument going on, right? Local compactness. It's not true. There's something to say. Okay. Okay. So this is less than or equal to this. But now we have a random object, and here we have a deterministic object. I want to show that this deterministic object is 0. So all I need to show is that this thing somehow is 0, or converges to 0, because I also have a t.
Okay. Can you explain again the last job?
Instead of c, which goes over all possible complex numbers, I plugged in a specific complex number. And this is infimum, so it's less than that.
We're assuming that omega is plugged, right?
Yeah, omega is in there. Omega is in. This is true for, So this is true for every omega in the ambient probability space. Okay, and every t, yeah. So here I should write for every t, almost surely is false. Okay, but it's not even almost surely, it's really pointwise every omega. Okay. Now, what is this thing? What I'm going to show you is that this thing converges to zero in some mode of convergence, which means that the only way that the only number that can bound it from below, pointwise, is zero. Okay? And I'm going to show that it converges to zero in probability. Okay? So what can we say? Yeah. What can we say about this thing?
If you have convergence in probability, then you have subsequent convergence almost surely, right?
Sorry?
If you have convergence in probability, then you have a subsequence that converges almost surely. and
Yeah. Okay. In fact, we can do L1. We can do L1. I don't know why I'm saying probability. Okay, let's see what we're going to use martingale convergence. Okay. So now this fxt, this is a bounded martingale. Why? Because I took bounded harmonic function. Okay. So it converges almost surely and in L1 because it's bounded, so it converges also
Uniform integral.
uniform integral.
Because it's bounded and because it's a harmonic, right?
Yeah. Harmonic function is the martingale when you evaluate the random walk, and we talked about that, right?
We didn't say it explicitly, but
Yeah.
We didn't?
Okay.
Okay.
Not sure.
that's in another course, but we didn't say it.
Yeah.
Okay.
We can say it and then prove it.
Okay, so I should have done it. So now I have to do it after this. We will see that this is always a martingale, but it's bounded because the function is bounded. Okay. So this I still need to prove. We will prove it. So it converges because any bounded martingale is a uniformly integrable martingale. It converges in L1 and almost surely to some limit. Okay. L. I don't know what the limit is. Specifically, also fxt plus k for any k, for any n, let's do n, for any n, fxt plus n also converges to the same limit, right? It's a subsequence. And so this, and so fxt plus n minus fxt converges what I want now in L1 to 0. L1 to 0. Now I don't want fxt plus n, I rather want this. You see, if I show that this converges in L1 to 0, right? And I take expectation here. Okay. Yeah, so because B is finite, if I take if I show that this converges in L1 to 0, then the maximum is finitely many will also converge in L1 to 0 because it's bounded by the sum.
And also just take expectation on all sides, right? And then get the number.
No, but then the maximum is inside the expectation. You have to be careful. I bounded by the sum because it's a finite set. Otherwise, I didn't use the fact that B was finite. Maybe take maximum, just L infinity norm. Could have done it. Right? Where am I using the fact that B is finite? B is finite comes from the fact of finite dimension, and I need to use that. Okay? So we have to be careful, but I will do L1. Okay? So we have this converging to 0. Now I want you to notice that what is the expectation of this thing? Sorry. Read. First, I'm going to take, so this was true for any n. Do any n I want, right? So we're going to choose n, so fix x in B. Okay? Yeah. Fix x in B and take alpha, which depends on x, and n, which depends on x, such that the probability that xn is equal to x when you start from the origin, okay, this is at least alpha, which is bigger than 0. Okay, what is this? This is just adapted. I'm just using the fact that mu is adapted. Right? There is some time so that I can get to x. can get to any element with some positive probability.
Adapted is that the matrix is irreducible?
What?
Adapted means the matrix is irreducible?
Yeah, that's what we said mu is adapted, right? We always take, that was symmetric, adapted, we took measures symmetric. So you see, I'm using the fact that mu is adapted. I think that's the only thing we need for this theorem to work. Symmetric and the exponential tail are not important. Okay, now what does this, well, so once I have this n, right? What I can do is I can bound this below. This is an expectation of a non-negative thing, put indicators inside. Okay, so I bound it below. This xt plus n minus fxt indicator that xt plus n is equal to xt times x. This is I'm allowed to do. I just put in something which is at most 1 times non-negative, so just pointwise inequality. So inside the expectation is fine. But I want you to notice that what's the probability of this guy? Right? This is alpha, right? Conditioned on xt, what is the probability that in the next n steps I do xt, I get to xtx? It's just the probability that n steps do x, which is alpha.
This is the Markov property.
Exactly, it's a strong, well, it's a Markov property, and I can condition on this. So this expectation, I can condition it. Okay, I'm going to condition it on xt or on the sigma algebra up to time t, right? So if I condition everything here, okay, first of all, when I have this indicator, I can replace this with xtx, right? So here I have xtx minus fxt in absolute value. I have to put in the indicator. Okay, let me write this indicator a bit differently. This is xt to the minus 1 times xt plus n equals x. This is the same indicator, right? And then I took two expectations because here I want to condition on ft. Why do I want to condition on ft? I want you to notice what's going on. Conditioned on ft meaning all the information up to time t. Condition of ft, this is, what is this? This is a new Markov chain, right? Starts from the origin and is independent of this information. Right? It's just what I do after time t as if I started from the origin, right? It's what I multiply. This is what I need to multiply xt by to get to the future. Okay? So this is just, this is independent of ft, okay? This is measurable with respect to ft. So it comes out of the conditional expectation. You just get the conditional probability of this with respect to ft, but it's independent. It just gives you that number.
Why is it independent on FT? Because you need to know where you have started, right?
So this is just equal. So what I just said is that the probability that xt minus 1 xt plus n equals x conditioned on ft, this is almost surely equal to the probability you start from nothing that xn is x. Same number. Because how do you continue from xt? Maybe you want to think you continue n steps, you get to where you were times x. Okay?
But can't xn be dependent on ft?
No, but this is a different xn. I mean, here you're looking at t plus n. It's in the n steps in the future. The number you get here is always this number. The number of n steps. It's just this is the Markov property. I know where I am at time t, xt. I want to get to xt times x. What does that mean? I want to go from here to something times x. So I want to do my next n steps need to multiply by x. As if they don't know that they don't know about this, because the groups you
Part
can
of translation, right?
yes, translation. The groups you can do a translation.
Remind what is expected to conditional probability on substitution.
Conditional probability is just the expectation of the indicator. Conditional expectation of the indicator is what is written there. So this guy comes out, right? This becomes the probability. This probability is a number. There's no more conditional expectation. This number comes out of the expectation, and what we get is that this is at least, right? We have the original expectation. This is the game we're playing, times that number, which is at least alpha, okay? right? So delete alpha. Okay. Now we have to be careful. Yeah. So this thing was converging to 0. Right? Because that's what we just said, they converge to 0 and 1. This is some constant number depending only on fixed x and n. That means that this thing has to converge to 0 as well. And that was true for every x and b. Okay? That was true for every x and b. So now I continue this guy, right? So when I take expectations over everything, let me change color so that I can still fit it on the board. So you see where I am. So, right, so I'm continuing this computation in here, sorry for the mess. Okay, just so that everything, we had this inequality, right, between this and this. And so I get that the number that I'm looking at, which I want to be 0, is less than or well, this number in expectation, but the expectation of a number is a number, right? There's no randomness on this side. That's the whole thing here. Okay, is less than the expectation of fxt, or not that at all. Not that at all. It's less than the, here you have to be careful. Okay, there's a constant c, and there's an expectation of a maximum of x and b of this thing. Now there are a few ways to proceed. One would be to say, I know that that sequence, okay,
You know, there is one x in which the maximum is obtained, and you prove this one for every x, so just take this x, right?
well, for every t, it's a different x, and then you have to say that there's one x that's good for infinitely many t.
Yeah, right,
Yeah,
you take it
okay.
for every-
But I don't want to do that. It's much easier because b is finite. All I have to do is I have to say that this is less than or equals c, sum over all x and b. Maximum is always less than a sum of non-negative things, right? And sum expectation is linear. Then I have expectation of fxt x minus fxt. Right, and now you can just say each one of the finite terms converges to 0, so the whole sum converges to 0, right? This sum converges to 0 as t goes to infinity. Everything was about numbers here, so this number has to be 0. That number has to be 0 basically means that you have to have a constant. Okay, you can check that. What it means is that check that implies the function is constant. Okay, so we proved that if the dimension is finite, then we use the finite dimension heavily to get this b here. This was not true if we didn't use finite dimension.
I know that I know from Yair that this dimension, if it's infinite, then it's
Countable.
uncountable. This proof can be like generalized to zero.
No. I don't see how you can get anything by assuming countable. There, the uncountability comes there. There it comes from like these bare category statements, which kind of you can't even see here. There you have a convex space, Millman, you do some. I would need like a heavier thing. This might be a convergence, not you know. And in fact, the method here is more important than the actual result in a sense, because first of all, I can give you an exercise. You can take this proof and you can make it work for other spaces. For example, you can take this proof and you can make it work for the situation where you have what did we use? We just used martingale convergence. I did use the fact that it converges in L1. So I needed uniform integrability, but I could have worked with convergence probability or done other things. So I could have used only almost row convergence, okay? And what I would say is that so all I needed was that this difference converges to 0 almost surely. That's all I need. Okay, or even in probability. Okay, it it converges to zero in probability, it would mean that this sequence would converge to zero in probability, which would tell me that the probability that this maximum is bigger than epsilon converges to zero, which would tell me that the probability that this number is bigger than epsilon is zero. So that number cannot be, and there's no probability, right? That's just a number. So it would just tell me that the event or set, if that number has to be zero. So all you need is that this converges to zero, and that you can also do with positive harmonic functions. Now the question is, what is the dimension here? What does dimension mean? So you can think of how to turn this into a proof. Suppose, imagine you have a space. What did we use here? What did we actually use here? We used a few things. We used that we have a space of functions, a vector space of functions of finite dimension, right? Such that in the space, for any function in the space, this difference goes to zero. Okay, enough to say that for any basis element that goes to zero. Okay, in probability even. Okay, and such that the space was invariant to these shifts.
What do you mean for any?
We were able to do the shifts. Now, there's a problem because here I did norms and you have to do some other things. But you can take this idea and turn it into idea so that if you have a vector space of functions such that all functions have this property that things like when you evaluate them on random walks, not do with harmonicity, just that on random walks the differences converge to zero, and such that the space is invariant to the group action. So when you shift functions, you still stay in your space. Okay. Suppose inside that space you find, then that space has to be either just constants or infinite dimension.
I think what you said just solved the problem. You can do all this on the basis elements and prove the basis elements are.
No, but shifts don't preserve the basis. I get something else. I need to work with the whole space. Okay? Need to work with the whole space. Okay, so it basically tells you something about invariant finite dimensional invariant spaces, functions. They cannot converge along random walks in this sense. Okay, good.
For rating and then.
Now, a more sophisticated theorem would be to prove that if you have a bounded harmonic function, right, that, and it is true, and this is the first person I know. What?
Wanted to explain why bounded, why f of
Oh,
x
bounded
is
martingale. Yeah. So one more remark, and then I'll explain why it's bounded martingale. So just the first person I will prove it is Alan Kahn, actually. So nobody thought of phrasing it this way. If you have a bounded harmonic function f, and you look at xtx. So if I look at f of xt, I'm going to explain in a second why it's a bounded martingale. This is not a martingale. It is bounded, but it's not a martingale. But Alan proves that this thing has to converge almost surely to some random limit, not deterministically. Okay? It has to converge almost surely to some. Then you know that I rather using some argument like this, if it's adapted, then you know, has to coincide infinitely many times with the original thing, so they converge to the same limit. But we could have also used that. We could have maybe also used that. Okay. The only way I know how to prove this, well, Alga gives some proof, which I thought about because I didn't understand her proof, so I tried to think about a different proof. But basically, it's the same proof, but phrased in a different language. So you can take this as an exercise. It's an interesting exercise to try to prove it. Use the up-crossing lemma. Take this sequence. Remember, how did we prove martingale convergence? We proved that the number of up-crossings was finite almost surely for any given interval. Do the same thing here. Prove that the number of up-crossings for this process, this is a real valued process, right? I mean, okay, take real valued functions. And use complex, you just split them into real and imaginary parts. So take a real valued bounded function, you look at this thing, and you show that the up-crossings, the number of up-crossings is finite almost surely.
Or fixed x.
So the lim sup and the lim inf, right? They have to coincide. Okay. So if you look at that, and how can you determine the upcrossing, right? What we showed in martingale pointer, not just that the upcrossings are almost surely finite, rather they have the number of upcrossings has finite expectation. Right? We can bound the expectation by some finite number, and which depends on the interval and whatever, but the smaller interval, the bigger that number gets. But you always, for every given interval, you have a finite bound on the expectation. And how many times is this going to upcross an interval, right? Basically, you always have a chance that this guy is this guy, right? Even if you condition on where you are at xt, there's always a alpha chance that this is the same one, right? So you kind of get that in expectation, the number of upcrossings of this guy and the number of upcrossings of this guy should be basically the same, the expected number of upcrossings, up to maybe a multiplicative constant. This is kind of what we did here, right? We take the expectation, we did some games, and we got that the two sequences are basically the same up to some constant. Okay? So that's why if one goes to 0, the other goes to 0. Same thing you do here. You bound the number of upcrossings of this by the number of upcrossings of that. This we know that the expected number of upcrossings is finite because it's a martingale. It's a uniform integral martingale. Okay? Not just finite in expectation. Okay? So you can use that to do this. And interesting. I mean, it takes some work. It's not like a 5-minute exercise. But I just wanted to explain that there is some idea here how you can get things. This trick of looking at these things and martingales and upcrossings and things like that gives you a lot of power. You can prove a lot of things. I don't know any other proof that doesn't use martingales to prove that. I mean, even Alenka's proof in the background, there is a martingale hiding. Okay, so I don't know any non-probabilistic proof of that fact. Now I'm going to explain why this is a martingale, why it's a bounded martingale, or why harmonic functions in general give you martingales. In fact, why does a probabilist want to talk about harmonic functions? Ashila?
הוא אמר לי להשתמש בלמה הזאת בתזה, זה מה שאריק קרא.
כן, עומר משתמש בה, משם אני יודע כי הוא בא לדבר איתי. Well, we should give Alenka the credit. I mean, it's her idea, her...
לא ידעו את זה לפני?
אני לא שמעתי את זה. Okay, here's a exercise. Let's do an exercise together. We have G and we have mu. Okay. Then F is mu harmonic. If and only if fxt is a martingale okay, that's what I need to prove because bounded just comes from the fact that the function is bounded. Right, okay. It's a martingale what is xt? Xt is the mu random walk. Right? Remember what the mu random walk is, just multiplying by independent elements, right? Okay. So what do we need to prove?